Hi guys, this is Dr. Gonzalez, and this is your presentation on Anova, which is analysis of variance. This presentation is split into two parts. Your notes in Canvas, I believe, are one section. So you can download your notes, print them out if you need to or whatever, and then there are two videos that go with this. So what is an Anova? So ANOVA is an abbreviation that stands for analysis of variance. Okay, remember variance is how spread out certain things are. So ANOVA is a statistical test that we use when we want to compare the means of three or more groups to see if at least one of those groups is different from the others. So you have this graphic down here with frequency and value, and I've got three distributions and I've got three different means. So I want to see the variance between one of these combinations to see if that specific distribution is different from another based on its mean. So what do we use an ANOVA for? So an ANOVA is really good for telling if there are differences between group means, and those differences aren't just due to random chance. So this is where we're getting into treatment effects or conditions and whether or not that effect that you see is actually an effect or if it's due to just random chance. So here I have I have three distributions, like I was talking about, three different means that I'm comparing. Perhaps I'm comparing group one. They have 10 milligrams of a drug called Neurovive, which I believe I made up last time, and it was like an ADHD medication. And then my second group, I'm going to compare 20 milligrams because I'm trying to see if there is a difference in those conditions, right? And then I'm going to have a placebo group because in a research study like this, it's really important to have that group that doesn't receive any treatment so that you have baseline and you have something to compare it to when you're looking at those other means. So remember, we're going to just hit this again because it's really important. Every experiment has to have, at minimum, one independent and one dependent variable, okay? And we got to have them defined and operationalized because you can't come up with a treatment effect if you're not really sure what your treatment is to begin with. And sometimes we might have controls or placebo groups because those are important depending on our design. So remember your dependent variable, it's got to be both observable and measurable. I've got to be able to see it, and I've got in some way, not necessarily physically with my eyes, but I've got to be able to see it and measure it. And our independent variable has to be manipulated. If it's not manipulated, then you do not have a true research study. And this is really important because this is going to get into our ANOVA here. An independent variable that has different levels, we might call those things conditions, okay? In a t-test, I might have two levels or conditions, and maybe I am just comparing 10 milligrams of a drug to a control group with no drug. In an ANOVA, I'm going to take that one step further. So I'm going to have three or more conditions. So I can't necessarily test three or more conditions with a t-test. You can do it, but there's some things we're going to talk about that would limit that ability. But an ANOVA is going to take into consideration that I am looking at three or more conditions, and it controls for those issues you might have if you just did a bunch of multiple t-tests. So three more conditions, an example would be 10 milligrams of the drug, 20 milligrams, and then that placebo group or no drug. So let's go over some examples of some variables that are now broken down into conditions. So let's put ourselves in the shoes of some researchers and think about how they might operationalize an independent variable into three or more groups. So I have a therapist might use type of therapy. They may look at cognitive behavioral therapy, CBT, versus mindfulness versus no therapy whatsoever. That's my baseline right here. My no treatment group, my control group. Maybe I'm looking at task after a certain amount of sleep. And so I quantify amount of sleep into 4, 6, or 8 hours. Maybe I'm looking at whether or not you study better with music. So I have classical, R&B, banda, and no music. Maybe I'm looking at a group of children and ADHD behaviors. So maybe I have a group that's getting positive reinforcement, a group that's getting negative reinforcement, and then a group that's getting no reinforcement at all, which would be really sad. Maybe I'm looking at how to induce stress in different conditions. So maybe I have a low stress task, a high stress task, and then a group that does nothing and just takes my assessment. I might compare different medications. So I could test the ADHD medications, Adderall, Vyvanse, and then no medication. Maybe I'm looking at the type of diet, low carb, paleo, vegan. I might look at treatment setting where a particular type of alcohol treatment intervention is taking place. It may take place inpatient, outpatient, at an intensive outpatient setting, or at home. Going back to one of our course favorites, screen time before bed, 2 hours, 1 hour, and none. I might look at coffee consumption, 3 cups, 2 cups, no cups. And then maybe if you're in education, you might be looking at the type of classroom environment. You might be dealing with a traditional lecture, a flipped classroom, or an online situation. All right, so why wouldn't we do just a bunch of multiple t-tests? If I had 3 or more groups that I wanted to compare them, a t-test was pretty simple, right? It didn't take a lot of intense work to do that. Well, a t-test compares to sample means, not the variance, okay? When you run multiple t-tests, every time you do that, you increase your chance of making a type 1 error. Remember, a type 1 error is a false positive. So that's when you say there is an effect and there really isn't. So it's not a good thing, right? If you're out there claiming that your therapy was effective and it really wasn't, then, you're not in a good position. So we're not going to do multiple t-tests because the number one reason is it increases type 1 error. So let's examine what that really means. So why is it so bad? Let's suppose we're looking at a study where we want to examine those types of therapy we talked about earlier in my example of the different conditions, and we're treating anxiety. So your basic research question might be, which therapy is most effective at reducing anxiety? So you set up your experiment. You've got 3 conditions of that independent variable. You're going to look at cognitive behavioral therapy, CBT, a group that is working with mindfulness, and then a group that's not getting any treatment. That's just our control group. So you decide you're going to compare those conditions using t-tests. So in order to make sure you're comparing all of your different conditions to each other, we're going to need to run 3 specific kind of trials, right? I've got to compare CBT with mindfulness. I've got to compare CBT to the control. And then I've also got to compare the mindfulness to the control. So at minimum, we've got to do 3 separate tests to make sure we're getting all of our comparisons done. Now, imagine that each one of those tests has a 5% chance of creating a false positive. Remember, false positive is I say there is an effect when there really isn't one. So if one test has a 5% chance of a false positive, what happens when you're running 3? So you are probably thinking, okay, if only one causes a 5% chance, then I'm going to be increasing that risk by adding more. And you're exactly right. When you run 3 tests, you're looking at that risk increasing to 14%. Now, you might think, well, 14% is not so bad. Maybe I can make this work, right? Well, it gets worse when you have more than 3 conditions. It gets dramatically worse. So 4 conditions would need 6 comparisons to make all of your specific things that you want to examine, right? So your type 1 error risk is going to increase to about 26%. And so now you're looking at a 1 in 4 chance that you're saying there is a treatment effect when there really isn't. Now, let's go even worse because, there are situations out there in the research world where you are going to want to have up to maybe 5 groups, okay? And that is going to need 10 comparisons to be able to do that, 10 t-tests that are going to cover all of the different combinations that you want to look at. And when you do that, you are carrying a 40% chance of a false positive. So now we've almost reached a situation where 1 out of every 2 chances of getting a false positive is going to happen. That pretty much negates the whole purpose of doing any of this. Your statistics are just they're duds now. You can't do that. So why would you even want to do any t-test at all? Well, that's where Anova comes in. All right, that's where Anova comes in. So let's go over the different types of Anova because there are a lot of them, and there are only a couple that I'm going to require that you really master with Jamovi, because Jamovi in and of itself is also limited to what kinds of Anova that you can do because it's a basic free crowdsourced sort of statistical analysis program. So we're not going to learn something that we're not going to really need to worry about at this point in our research game. Okay. So a one-way ANOVA is the basic, right? It's your entry level here. So a one-way ANOVA is going to compare the means of 3 or more groups, and we're going to look at one independent variable, but that independent variable it's going to have multiple levels. Okay. Now I can also do a two-way ANOVA, and in a two-way ANOVA, I am going to look at 2 independent variables and how they are impacting the dependent variable. And I want to know something that's called an interaction effect between them. And I'm going to explain that a little bit more in a few moments. We also have a between subjects ANOVA and a mixed model. Between subjects is when we're going to compare group means. But remember, each participant is only in one condition. So I got to have independent groups. So I can have a one-way between subjects ANOVA. I can also have a mixed model. And in a mixed model, I'm going to combine that between subjects design with within subject variables, and I'm just going to do one analysis. And so it's going to look at what we call group and time related effects. We're not going to get into mixed models. I just want you to understand that there are models out there that can mix that between and within subjects to really get some really advanced, interesting analyses that you can run. Basically, the sky's the limit. We also have ANCOVA and MANOVA. So an ANCOVA is an analysis of covariance, And that is when we adjust for the influence of another continuous variable that is out there doing a control. We call that a covariate. And we're going to compare group means on that main dependent variable while we adjust for that other variable that might be messing around with things out there. We also have Anova, which is a multivariate analysis of variance. And that tests for group differences across two or more dependent variables simultaneously to see if patterns occur. You might also hear out there Mancova, which is a multivariate covariant analysis of variance. It's even more complicated. I just want you to know there's a difference between Manova and Mancova. And right now we're just going to focus on that multivariate analysis of variance. And I'm going to give you some examples of what that looks like in just a moment. So ANOVAs are really versatile. We can use them in lots of different experimental designs. That's what's really cool about them. I can't get this level of flexibility with t-tests. T-tests are great. They're super simple. And you would be surprised at how much research is going on out there in serious, really cutting edge research that is being done with a t-test. But like we just looked, you can't compare multiple conditions or levels of that independent variable with those t-tests because it just inflates your risk of that type 1 error way too much. But I can look at different factors, which we call those independent variables. So factors is another word for independent variables. And I can also base my design on the number of groups that I have and how those participants are assigned to conditions. Because remember, the gold standard is random assignment. So like we just touched on in the last slide, in the language of ANOVA, a factor is another word for an independent variable. So your experimental design that is based on factors might include a single or a two-factor design. So in a single factor design, I've got one independent variable. So down here I have type of therapy, CBT, mindfulness, and that control. That's single factor, straight up, entry level there. But maybe I'm interested in how therapy and gender work together. So I'm going to introduce that two-factor design here where I have two independent variables, okay? I am manipulating the type of therapy, and I'm assigning people, which is a form of manipulation, based on their biological sex or gender, just male or female. So remember, in comparison, what can a t-test do? It can only examine a single factor. So our experimental design can be selected based on how those participants we have experience those different conditions. Remember, we have independent measures. That's where we use different groups of people for each condition. So if you're a participant, you are in one group, one level of that independent variable, and that's it. You only experience CBT if you're in the CBT group. You only experience mindfulness if you're in group 2. You only are acting as a control and getting no therapy in group 3. But remember, I also have the within subjects repeated measures. So this is when I use the same group of people in all conditions. And remember, one of the advantages for that is that you don't have to recruit as many people. So if you're dealing with a particular population that is limited in your ability to recruit them, you might have to use repeated measures because you're limited in the number of participants. So maybe I recruit 75 participants for my research study. This is the therapy one again. But instead of assigning people or participants to one group only, I'm going to do all 3 conditions with each individual participant. So you might have phase 1 where they go through 4 months of CBT. You might have phase 2 where they go through 4 months of mindfulness, and then phase 3 where they have 4 months of no therapy. And this is just an example. This is probably not the most ideal way to do therapy. I am not a clinician, so it's just an example here. All right, so let's look at what some of these particular situations look like. So a single factor independent measures design. In this particular design, I have a research question that is saying, does the type of family pet influence household stress? So the independent variable that I'm testing here is type of pet, and I'm going to have 4 levels. I'm going to have a control group that gets no pet whatsoever, and then I'm going to have a dog, a cat, and a ferret. And what I'm going to do is I'm going to somehow have these groups that get their pet, and I'm going to record household stress. I'm going to use a perceived stress scale, and I'm going to give that to their families after they've had their pet for 2 months. And I kind of thought this is like kind of a neat research study to imagine, because getting a pet is such a wonderful experience, especially when you've got kids, right? They want pets. But especially for adults, when the kids don't, pick up and take care of the pet, it can actually increase, in my thought process here, the stress of the adults in the household. They've got another living thing that they're responsible for. So what kind of study would that be? This is our family pet and household stress research study, and that would be a between subjects, independent measures design, and it is using a one-way Anova. So let's look at a repeated measures design. So a research question that might be answered using this type of design would be something like this. Does the type of background sound affect creative thinking performance? So I'm going to be testing you on some sort of creative thinking task, okay? And I want to know how you perform on that task. And you're going to be listening to different kinds of background sounds, or there are going to be background sounds back there. And I'm going to be looking at how well you did. So I'm going to have 4 levels of those background sounds. Silence, my control, white noise, rain, and then I'm going to get a selection of random YouTube videos that are audio only. And I'm going to somehow set it up to where my algorithm is just spitting out the most random YouTube videos. So you might get one that's a little crazy and it's not really calming. And then you might get something that is. I don't know. But my dependent variable, the thing that I'm going to be measuring, is that creativity score. And I'm going to use, this is a measure that I found out there, remote associates test, the RAT test, which is a measure of creativity. So what kind of study would that be? That is a within subjects, independent measures design using a one-way Anova. I still haven't added another manipulated variable yet. That's where you get into two-way. So let's look at that. So we're going to kick it up a notch here. So look at this research question. How do type of pet and home size affect the anxiety levels in adults? So imagine that situation I said earlier where you've got a new pet. Now this time, imagine the people that you live with and the space that you occupy. Are you in a small home, a large home, a medium-sized home? So I'm looking at type of pet and the size of your home. And I'm measuring stress. So this is going to be a 2-factor independent measures design. So let's break it down and look at the different components of that. How would it look? So my research question, How does the type of pet and home size affect the anxiety level in adults? I have two independent variables this time. I have type of pet with 3 levels, dog, cat, and ferret. And then I have the size of the home, and I'm going to measure that in square footage. So a small home might be less than 800 square feet. That might be a studio or maybe a one-bedroom apartment. Medium would be 800 to 1600 square feet. So that would be like a townhouse, a condo, an apartment, a small house. And you can see here where the number of bedrooms might be different. And what you might think is something small might actually, like a one bedroom apartment, might be luxurious based on square footage. So I just wanted you to kind of see the variability here. I wanted to measure home size in something that was very, very specific. So I went with square footage. So our dependent variable here, we're going to look at the generalized anxiety score of our participants. We're going to use the GAD-7. And this would actually be what we call a 3x3 between subjects factorial ANOVA. Because each participant is going to be randomly assigned to one pet type, and it's going to fall into one home size category. So what I would probably do is when I recruit my participants into the study, I'm going to classify them based on their square footage of their home, and then I'm going to randomly assign them to a pet group. So it's kind of it's a mixed type of sampling. We are specifically looking for people with certain traits and putting them in groups, which would be the home size. But then once we have those strata out there, we're going to do our random assignment so that we make sure that we are following as much as we can about our research design to get the best results. So what is the specific design that I just showed you? What is it testing? Well, it's going to test 3 things. Remember, this is where you get what we call an interaction effect. So obviously I'm looking at pet type. So does the participant's anxiety level vary depending on the kind of pet they have, regardless of what size their home is? So we're just looking at ferret versus cat versus dog. At the same time, I'm going to be looking at the main effect of home size. Does overall living space affect generalized anxiety regardless of pet? You might have 5 people crammed into a one-bedroom apartment. That in and of itself might be stressful. Okay, so I'm going to look at that home size without looking at pets, and I'm going to look at pets without looking at home size. But at the same time, I'm going to look at what's called an interaction effect. And that interaction effect is kind of the product of both of those independent variables together. So an example of a question that you would answer in this particular scenario would be, does the effective pet, the kind of pet you've got, does the effective pet type on anxiety depend on how large or small the home is? So what I was trying to get at here was, maybe you've got a dog and you're living in a one-bedroom apartment with 4 other people. So the idea is you're already stressed out, your anxiety's probably already through the roof, and now added a dog to that mix. So, all right. Another example might be a ferret and a small face. I've never had a ferret, but from what I understand, they can be quite, you know, energetic. That ferret in a small space might create very high anxiety, especially if you've got multiple people in there with you too. So that's another variable I could even add to it. If I really wanted to get funky with it, would be add like how many people are living in your house. But anyway, at the same time, that ferret in a bigger home might be more manageable. And then again, it might not. He might go hide somewhere where you can't find him. I have no idea. So we're going to stop this presentation here. This is kind of just an introduction to the different kinds of designs that we have with Anova. So the focus in this course, I really want you to get, I've said this multiple times, is how do I go out and do these analyses using the tools that I have available to me? And so I'm going to end this presentation, and I want you to get ready to play with some data, because in the next part 2, we're going to calculate how to do several of these different designs. All right, so let's continue. We were talking about the two-factor mixed model. I think I ended the slides on the last slide with the audio, but then I discovered I had more slides, so ignore whatever mistake I made there. But how would we change our model to make it a mixed model? So all you'd have to do here is change it to where each subject experienced all 3 pets. So hang with me here. This is going to take a little bit of mind warping, and it would not be an ideal research situation, but it was the best I could come up with. So imagine that each individual participant experienced all 3 pets. That would make it mixed. Now, like I said, this is not ideal. So you would start with the participant with a cat. They would do their week with the cat. You do your GAD-7 measurement. You'd move on. The next week, they'd get a different pet. This time, they're going to get a dog for 7 days. And then after those 7 days, you would measure their GAD-7. And then last, you would finish with a ferret. That would be your last week. So each participant is going to experience all 3 conditions, and that makes it a mixed model. So ANCOVA is an analysis of covariance, and it's similar to Anova, but it's going to compare group means while at the same time controlling for the effect of another variable, and we call that other variable a covariate. That ANCOVA is going to test whether there is a significant difference between those groups on your dependent measure, and it's going to remove the influence of that covariate variable, because in the end, that variable may be actually affecting your outcome. So we want to control for it. So ANCOVA is a blend of Anova and regression. We're going to we cover regression in non-experimental statistics. So we're not going to hit on it very much in here, but remember, regression and all that, when it works together with Anova, it evaluates the means of your dependent variable across different levels, just like an independent, just like a t-test would do, but and like an Anova here, but at the same time, you're going to control for those covariates. And a covariate is an independent variable that may actually be impacting your dependent variable in your study, but you're not interested in studying it right now. So an ANCOVA is a good design when you can't control for certain factors physically. So it's kind of like I'm going to control for them statistically. So let's look at an example so you can get a good feel for what an ANCOVA design would look like. So imagine that like at my high school where I teach, I taught a morning and an afternoon class at my alternative school. And I want to know if my presentation method is impacting my students' learning, and I'm going to look at that learning through their test scores on the state biology test, right? A high stakes test that we have to teach. It's a required subject. Kids got to pass the test to graduate. So it's a big deal, right? So I'm going to use 2 different kinds of instruction. I'm going to use live instruction in the morning, where I actually get up, physically talk to the kids, teach, write on the board, all that kind of stuff. And then I'm going to record that video of me teaching in the morning, and I'm going to play that for my afternoon class. So they're not going to have the interactive factor of the teacher there. It's just whatever happens in the video happens, kind of like these videos here, right? But the problem that I would be worried about is that there are some variables that may automatically affect my morning class and make them different, so to speak, than the kids or the students in that afternoon class. So I want to measure those other factors and I want to include them as covariates because they might help me explain some phenomena that I find out there that I'm not really interested in studying right now, but I'm controlling, like I'm watching it, right? So, for example, one thing I would be concerned about in this research design would be that my morning students are sleepy. That's just a fact of life. First period classes tend to, you know, kind of drag their feet. Nobody wants to take an 8 a.m. class in college either. So, when you're walking in with that disadvantage already, you're sleepy. How do I know that my presentation method, how do I know if I got a difference, if it was because of my presentation method or if it was because they were sleepy? Well, I'm going to control for it. So a couple of other, I put student sleepiness. So I'm looking at presentation method right here. I'm looking at presentation method, but at the same time, I'm looking at student sleepiness because I want to see what's going on right there. Well, that's not even the only variable, covariate actually, that I could be worried about. Um, at the alternative school, I'm always fighting student motivation. Kids don't want to be there. They're sent there on purpose. They did something, and this is a consequence to their behavior. So I'm already fighting a battle with that. So ill motivated students, sleepy students, I got to make sure I'm controlling for the things that I can control for so that I'm actually looking at, did my different delivery methods of instruction have something to do with this? So here is my in-person pre versus my pre-recorded video there. Same thing here. All right, so let's look at MANOVA. MANOVA is multivariate analysis of variance. So this is when we test whether our groups differ across multiple related outcome variables while accounting for the relationships between those outcomes. So I'm going to give you a really good example of this in a minute, and you're going to go, I got it now. I understand. So it's like an Anova, but instead of testing one dependent variable, I'm going to test two or more, and I'm going to do it at the same time. So go back to your therapy research question that we had earlier in the lecture. So what if you wanted to compare three types of therapy: CBT, mindfulness, and a control group, right? I want to measure anxiety and depression as my dependent variables. And the reason why I'd like to do that is because anxiety and depression go together. They are comorbidities. So there are things in psychology, psychiatry, even in medicine that go together. They're comorbid. Those two things happen at the same time. And it's very difficult sometimes to determine what effect or impact one of them is having on something else because they're so intricately entwined, like type 2 diabetes and being overweight. Okay, so I could run two separate ANOVAs, but that's going to do the same thing that would happen with my multiple t-tests. I'm going to start increasing my type 1 error. So I'm going to use MANOVA to see if there is a combined effect of therapy on both of those mental health outcomes, on anxiety and depression at the same time. So what it's actually going to do is it's going to control for correlation between those two variables. Again, anxiety and depression are usually correlated with one another. As one changes, the other one does as well. If you treat anxiety, you may be treating depression. If you treat depression, you might be actually treating anxiety too. So that MANOVA is going to help prevent those issues with inflating my type 1 error. Remember, those are your false positives. And that would be what I would encounter if I ran multiple ANOVAs, just like if I had ran multiple t-tests instead of an ANOVA, right? But a MANOVA can do more. It can detect multivariate effects that you might not see if you were just looking at one dependent variable. So for now, you're probably going, okay, we've gone over lots of different designs here. What in the heck am I going to be doing on my assignment? This is crazy. For now, you are going to focus on single factor independent measures designs. We are not going to do all of those different designs in Jamovi. I believe my intention was to go over single factor independent measures designs and maybe repeated measures, but I still haven't decided. So right now, let's go over hypothesis testing again so we know where we are with that. So remember when we're doing a statistical test in this class, we've got our null and our alternative hypotheses. And we are pessimists, we go with the null. That's our baseline. And the baseline says there is no effect. There's no difference between the means of the populations. Okay? Any observed difference that we do come up with is going to be the result of chance or sampling error. So this is the way you would write your null hypothesis in simple terms. And the mu there stands for mean. So I read that as the null hypothesis states that mean 1 is equal to mean 2 is equal to mean 3. So in other words, all group means are equal. So my alternative hypothesis is going to say there's an alternative out there. I mean, there is a difference out there, but you're not going to be able to know where it is based just on your ANOVA. We'll talk more about that in just a minute. So my alternative says there is a difference between the means of the populations. The differences between sample means represents a real discernible difference in those populations that I drew those samples from. So my alternative hypothesis is simply going to state at least one group mean is significantly different from the others. So the catch is with hypothesis testing and ANOVA, I don't know where that condition is. I might have those 3 different means that I'm comparing from CBT, mindfulness, and the control. I run my ANOVA and I get an F statistic, and that F statistic says, hey, there is a significant difference between one or more of these means. The ANOVA doesn't tell me where it's at. Okay, but I can make my rejection or retention decision on my null hypothesis based on that F statistic. So if I reject the null, I'm saying there is a significant difference between those means. But that ANOVA isn't going to tell me which means are involved. So if I reject the null, if there is a significant difference in means between one or more groups, I'm going to follow up with what's called a post hoc test. And post hoc means it's done after the fact. And what I mean by after the fact is it's after I've done the ANOVA. So I have my null, I have my alternative, I run my test, my ANOVA comes up significant. I've got to follow that up with some specific tests to find where that significant difference is. What groups are we talking about? So we say that ANOVA is an omnibus test, which just means it's overall telling me that there is a difference and it's significant, but it's not telling me where that significance is. So let's go over some nasty math. All right, we're going to calculate, or I'm going to show you how one would calculate a single factor independent measures ANOVA. So what we're focusing on here is the F statistic, and an F statistic is simply a ratio. So let's look at it. So you might hear F ratio, F statistic, same thing. So that F ratio is comparing variability that is explained by our model, which is the experiment that we're running, compared to the error in the model, which is attributed to individual differences. So in other words, F is a ratio of the variance, get my highlighter here, the variance between your sample means and the variance that I would expect if there is no treatment effect. And we're going to go in the next few slides and we're going to start adding terms to this ratio so you can see how one would calculate this. Again, following up on what I just said, F ratio is a ratio. Your F statistic is a ratio. It's based on variance in place of sample means. Remember, a t-test uses sample means. We're using variance. So down here I have what a t statistic is. It's your obtained difference between your sample means divided by what I expected to see by chance. And F statistic is the variance between sample means over the variance that is expected by chance. So t-tests are based on differences in sample means. The F ratio, the F statistic, is based on variance between your sample means compared to what you expect to see in variance by chance. All right, so here we're breaking it down a little bit further. I have that formula that I just told you. F equals variance between sample means over the variance expected by chance. So I could have a situation where F equals large over small. So if that happens, I am going to reject my null hypothesis. That means there's a difference in my means out there. One of those means is an outlier, and it's causing that entire distribution to narrow, and it's going to be distinct from another distribution. I also have a situation where F is similar over similar. This is where I fail to reject the null hypothesis. Means are close or distributions overlap to the point where it's impossible for me to distinguish them apart. And then I have F small over large, and that is the situation where I also fail to reject the null hypothesis, but it's because those three distributions are so very close to that overall mean that overlap so much that the variance is unlikely to come from a separate group. So at the end of the day, our goal is to measure variability within Anova, right? And we want to explain the differences in scores. So I've got two graphs here, graph 1 and graph 2. In graph 1, look at your distributions. I have three means, mean 1, mean 2, mean 3. Distribution 1, distribution 2, distribution 3, and I'm looking at variance. And what you should notice here is that variance isn't overlapping, is it? I've got variance in one, variance in another, variance in a third, and there's only an itty bitty overlap down here. We're not even going to worry about that itty bitty bit. So in graph 1, your means are spread out, your variance is small, there's no overlap in the curves. But look at graph 2. Graph 2, I've got means again, and I'm looking at the overlap in the variance. See how this section right there overlaps with that section right there, and this itty bitty piece right here in the middle, I've got a confluence of those three different situations. So which graph would have a more reliable difference between the three curves? And if you guessed graph number 1, you would be correct. Because up here, I can tell that the variance in this first graph is attributed to that variable. I don't have this confluence of variance over here from two other sources that are messing things up. So in this example, that between samples variance, which is going to be important in that ratio for our F statistic in just a minute, that between samples variance is the difference, or actually the distance between those sample means, M1, M2, M3. And your within samples variance is the variance within each curve. So we have variance 1, variance 2, and variance 3. So how do you calculate that F ratio? Well, we have this cool little table right here, and this Anova table can be used to record the sums of squares and to organize the rest of the calculations if you so desire to do an F ratio by hand. There is a copy of this, I believe, in Canvas. It's really not that big of a deal. I don't think I'm going to ask you guys to calculate all this stuff. I've got some other priorities that I want you to focus on. But anyway, this table would be what you would use to calculate that F ratio, okay? So we've got to look at the source of the variation. It can either come from between the samples or from from within the samples. SS stands for sum of squares. So we have our sum of squares between and our sum of squares within, okay? And down here, your sum of squares 1 is going to be equal to those two things added together. Then we have our degrees of freedom, and degrees of freedom over here is going to get a little different from what you knew in the other one. So K minus 1, where K is the total number of groups. So maybe I have 3 groups. How do I calculate my degrees of freedom? It's going to show in just a minute, but I need to know that degrees of freedom between samples is K minus 1. So 3 minus 1 is 2. Right underneath that, I got my within samples variation. Here, I'm going to need N minus K. So N's the total number of participants. K is my total number of groups. Participants minus groups give me N minus K. Over here, I have my mean squares. It's the mean squares between and the mean squares within. And then I take these and substitute them in another slide. You'll see what I'm talking about. You get your F square, your F ratio. It's the mean squared between divided by the mean squared within. So your sums of squares and the degrees of freedom have to check to a few things here. You got to check for error. You got to attribute that. So you've got your SS sub factor, SS sub error, SS total. Okay. Or I can say the sums of squares between plus the sums of square within gives me my sums of square total. Easy, right? And this is just showing you the same thing for degrees of freedom. Okay. So here's where things get really interesting. You will not have to calculate these. I will provide them on the quiz. So if I give you the sums of squares between or within, you might need to calculate an F ratio that way, but you are not coming up from 0 on these things because that's not what we're here to do. So I've got sigma x here squared over n. All of this boils down to these are hard for people to remember. Let's substitute something for these formula. And down here you finally get to the sums of square within groups is equal to the sums of square total minus the sums of squares between. So this goes back to that source table. You've got your mean squares. You will see MS sub BG. It's the same thing as if I left off the G and said just B. G is between groups. B is between groups. So the mean squares between groups is equal to the sum of squares between groups divided by the degrees of freedom between groups. And the within groups mean squares is the sums of squares within groups divided by the degrees of freedom within group. And all of that takes us to the F ratio. Bam. The F ratio is the mean squares between groups divided by the mean squares within groups. So let's go and look at an example, because I don't know about you, but all of that stuff gave me a headache. Hang in with me. I promise you're going to get to a point where it's like, okay, I know how to do this. Don't worry. So let's set up our task here. So a researcher is exploring the differences between caffeine consumption and speed on a manual building task. Okay. So I'm going to give participants one of 3 caffeinated beverages. They can either get coffee, black, or tea, or an energy drink. And I'm going to let them consume those beverages. I'm going to let them chill for just a few minutes. And then I'm going to give them a small Lego toy, those little kits to put together. And I'm going to measure that assembly time on that task. So that's my dependent variable. How many minutes did it take for you to put together the Lego toy? So here's just a data table showing you some data for this. I have my energy drink, my black tea, and my coffee, and I just put some, some numbers in there. This is minutes. And what I'm going to do is I'm going to fill in that source table, and I'm going to get the sums of squares between groups is 33.6. Within groups, it's 10. And if I add that together, I get 43.6. Remember, K is the number of groups, and N is the sample size. So here I have my between groups, 2, 12, 14. My sums of squares, 33.6. 10 for within groups. I add that together and I get 43.6. And then I'm going to calculate my mean square. It's just this divided by that, right? So 33.6 divided by 2. Down here I have 10 divided by 12. And that's going to give me what I need to calculate my F ratio. Are you not seeing that this is going to be so much easier when you use a program like Jamovi to calculate this? I really hope you're seeing that, because honestly, when I took statistics as an undergraduate, we calculated all of this stuff by hand. And it was satisfying. If you like math, it gives you a good sense of satisfaction after a while when you've calculated all these things together. But at the same time, it can get really, really tedious. So I want you to be able to set this up and look at it through Jamovi and interpret it more than can you calculate all this stuff out by hand. There will be some hand calculations, but not all of this level. We're not taking it to the extreme here. So if I substituted in my formula, I would eventually get an F statistic of 20.2. All right, so there are several steps to determine significance, and I want you to pay very close attention, because there's a difference in calculating something out by hand and determining the level of significance versus using Jamovi or SPSS or whatever. Obviously, using a program is going to be much simpler, but I want you to know how you would find the critical values to be able to state your decision to make a choice about whether you're going to retain or reject the null. So the first step in determining significance is to establish what you are testing. You have your research question, but then you also have your null